Hey, it is a pleasure to be with all of you. My great privilege to be here. Thank you for that beautiful introduction, Rob. And as we get started here, I've got a little intro slide about me. It's really not about me. It's just why I'm involved in this space. It's true, I've got a class that teaches you how to do all this stuff, but the reason I'm involved in this space is not that class. That class came as a result of me being in this space. I'm the chief of operations for a managed security provider in the United States. And one of the things that I was very focused on as an operations person is anything that could be done to improve our business process, to allow our people to do their work better. Someone actually posted a question in the questions channel, and you're welcome to do that. I may not answer all of them while I'm going, because I actually have a lot to tell you today, but I will follow up on all of them afterward. James Dean was asking, so he saw the robot scanning the shelves in BJ's, and the question really is, are AI and machine learning developers concerned at all and doing anything to prevent AIs from taking humans' jobs? Are there no high school students who can do that job? And my answer to you, and I could be completely wrong, but my answer is no, they're not worried about that at all. And I very much agree with a statement that was made by another SANS faculty member. He said, it's not that AI is going to take your job, it's the person using AI who's going to take your job. AI, machine learning, is very good at very specific things. It's very narrowly intelligent. So it's really up to us to think about how can we use it to solve some very specific problems, which allows us to use our humans to do jobs that humans are better at than the machines. So that means that as a business, sure, I can put that robot in. I don't need the human to scan the inventory, which is actually wonderful. Humans hate doing that job. But that means I can get that human to do something else that needs to be done that the AI can't do. So that's really up to the business. That's just my opinion. In any event, that's where I'm coming from. That's what I started doing in our company. It's got to be about 10 years ago in trying to bring machine learning and AI into what we're doing for monitoring networks and doing threat hunting. And I want to talk a little bit about that. Threat hunting is obviously a really important buzzword these days. Everyone says they're doing threat hunting, and there are some things we do that we call threat hunting that really would not fit the definition of threat hunting for us, the definition we use in our enterprise. People tell me, yes, we have a threat hunting team. They're getting the threat intelligence reports. They're keeping up with the TTPs, the tactics, techniques, and procedures that are out there. They're using the IOCs that are being published, and they're turning them into detection capabilities. Those are beautiful things. But taking a known IOC and then seeing if you have that issue, okay, maybe that's on the edge of threat hunting. But to us, that's just good security operations. That's like updating your antivirus signatures. There's new malware, we update the signatures. There's a new IOC, we know how to look for it. Threat hunting to us is knowing how people are behaving. So that is the TTPs. That's understanding how our networks work, how our systems are used, how our users behave, understanding what's normal, and then thinking about what would abnormal look like. Can I begin to identify that? So threat hunting for us is continuously looking for unknown bad. And the way we do that changes. Sure, IOCs are great, but that IOC, as soon as it's published, is next to useless for your most advanced adversaries. We need to think about what they're doing next. We need to be creative in how we do threat hunting. I think of threat hunting, I think this statement is very true. The threat hunting is searching for the one important needle that's in the stack of needles. That's really what we're trying to do. How is it that we can leverage machine learning and AI? I've got two examples I'm going to give you here with demonstrations, but then I've got the first public announcement of a brand new thing that is coming to GitHub soon. So first, some demonstrations. Let me talk about some practical applications. Our first one is just going to be machine learning. So I'm not sure I would call this AI at all, although in the broad definition of AI, that is simply any system or process that can make a decision hopefully a good decision, based on input from its environment. The kind of decision of what we're going to do here doesn't really do things. It's deciding how to group things together. It really falls into the more specific bin inside of AI of machine learning. That is, any system or process that can continually improve based on feedback from its environment. So this machine learning, this AI, is going to learn how to look at DNS queries and to not make recommendations, but to help the human to do better analysis, using the machine to allow the human to do the human task better. For some context, there was a chief information security officer from a national lab here in the United States. I was talking to him at a conference. He was actually taking the applied machine learning class. And he began the discussion saying, I've got these data scientists working for me, and I've got all this DNS query data. Now, he's not talking about the queries people are running against his organization. He's talking about the queries people in the lab are making out to the internet. I've got all this query data, and I just have the sense that there is important intelligence information in there. I said, yes, I agree with you. I think there is. And then he said, these data scientists, I asked them what to do. Now, my data scientists here, I've got a little asterisk here because I'm not sure these were real data scientists. I think these were consultants playing the part of a data scientist because their response to me is a shocking response and not what I would expect a data scientist to say. They said the way you solve that problem is that you pay for threat intelligence lists. You subscribe, they'll send you lists of bad things, known bad, and then you see if you had any of the known bads. I was so disappointed. I was so excited when he had said he had data scientists involved, but that was so disappointing. And I told him, wait, because tomorrow morning, we're going to solve that problem. And that's what I'm going to show you right here. The get the threat intelligence list and see if you have known bad, that is clearly a SOC responsibility. What does that look like in terms of a machine learning solution? Well, let me switch over here. I've got some sample data. Let me get some of this loaded in here. So I've got these DNS logs. Now, the DNS logs that I'm using here are coming out of a tool called Zeek or Corelight. It's a network intelligence tool. It isn't smart. I mean, we say intelligence tool. It just generates information. It has a record of everything happening on your network, and it generates that out often into your SIM, though it could be into a flat file or into JSON, whatever you want it to be. It has everything about all the DNS queries that are occurring, when they happened, who made the query, what they asked for, if it resolved, what it came back to, the round trip time, everything you'd want to know. And what I'd like to do is see if I can apply a machine learning technique called clustering to this. This is unsupervised learning. And in fact, when you hear that term, it almost always means we're doing clustering. We're trying to see if the machine can find similarities between things. What am I going to cluster on, though? Now, there's a lot of things to cluster on. And I'm not saying that what I'm about to do is the right way. And I'm definitely not saying it's the only way, but it is definitely a valid approach and yields some very interesting results. What I'm focused on right now is, are there interesting patterns in the queries themselves? Some of you might be thinking, well, as you watch this, sure, that's interesting, but what about the round trip time? What about the size? What about the TTL? What about the... And those are all excellent things to additionally do the same kind of techniques with. But for now, I'm just going to be focusing on the name itself. So let me just do a little cleaning here. I'm going to drop out some fields that I know I absolutely don't need. And I've got a little bit of code here that's going to take the DNS queries and re-encode them. See, the issue is, one of the big challenges people face, I'd like to use machine learning, I'd like to use AI, but in order to do that, I have to understand how to represent my data in a way that a machine learning technique can make use of it. This is actually one of the reasons I think the LLMs are so incredibly popular. It is not the best AI we've ever created, but it's the AI solution that humans can talk to and get what it's doing without having to do all kinds of pre-processing and massaging to get it to work. Because those LLMs, they come at the end of many years of research. In fact, we've been building amazing AIs for at least the last 20 years. And all of the math, how all of it works, we've known all of that since the 80s. Now, true, the way we put that together in a large language model is a relatively new thing. But the issue leading up to the times we're in now is that prior to 2000, we just didn't have computers we could do that with unless we had mainframes. I actually think there's a potential for the reemergence of the mainframe market as a result of what's going on with AI, but that's a whole other conversation. In any event, one of the things I spend a lot of time with in the class that I teach is helping data scientists, so people who know the math, teaching data scientists how to take cyber data and turn it into something you can use in a machine learning model. Of course, the class is not for data scientists, it's for people like us. It's for cybersecurity people to learn how to apply these techniques. So I'm doing that here. I've decided I'm going to keep the length of the query. I'm going to keep the length of the domain name or of the suffix. I'm going to take the length of the domain name, the number of parts in the name. I'm just manufacturing numbers that describe that query, that move it into some high dimensional vector space. And I'm definitely losing information because I no longer have the actual query, but I end up with numbers that describe it. They describe some location where that is. And if I take that and I apply it to my data, I end up with, conveniently, a whole bunch of numbers, which is exactly what I need. Machine learning, AI, large language models can't cope with things that are not numbers. When you talk to ChatGPT or Bard or any of those models, when you type your input, the very first thing that happens is that that is broken up, turned into tokens, and the tokens are converted into numbers. It's all math. Now, looking at the numbers I have here, it's a valid question to wonder, is that a good representation of the data? There's an important thing to know about this space. Data science, particularly around machine learning and AI, this is an empirical science. Empirical. That word means it has to do with experimental. I'm going to demonstrate it works. We use that word because it sounds much better than we're just going to try some stuff and see how it turns out. But that's the truth of it. There is no right way. We're just going to try it. And if it works well, we're going to say it's right. The approach I'm going to use here is an approach called DB scan. That's actually what's happening in this cell right here. DB scan, a distance-based spatial clustering or density-based spatial clustering of applications with noise. None of that really matters. You don't need to remember that. What I love about this, now, in the organizations that we interface with that have some data science component, they have an analytics component, they're almost never using this. They tend to be using a thing called k-means that I really don't like. In k-means, for instance, we can do clustering, but to do it, the very first step is tell the algorithm how many clusters there are. If I knew how many clusters there were, I would not need the algorithm to cluster the data for me. Now, there's strategies we use to try to work out how many clusters there are. I'm very uncomfortable with all of that. I greatly prefer DB scan because with DB scan, it figures out how many clusters there are. And if there are things that are outliers, things that are not really part of a cluster, it identifies those things as outliers. That's perfect for me, especially when I'm doing cyber type operations. So I've already run it. It's already generated the classifications, and it has found 4 different clusters. So it's showing me here 0, 1, 2, 3. So those are 4 different clusters it's found. And I'm going to plot those in a minute, though the plotting doesn't really matter. And you may be noticing that there's this -1 here. It has found 4 clusters, and the items that are marked with a -1 are the things that are not in clusters. They're the outliers. Those are the anomalies. Now, when you and I hear anomalies as security people, we tend to think, that's bad. Anomalies are bad. Not necessarily here. It could be, but this is more like a statistical anomaly. It's a numerical anomaly. It's not necessarily bad. In the end, visualizing what this looks like, so here's how my data is clustered. Visualizing this is not important at all. People who come to the class, they start out, wow, I need to graph everything. But after 2 or 3 days, I rarely see people graphing things because you get much more comfortable working with the numbers. I tend to graph things when I have a lot of them and I'm doing an experiment I want to understand better, or I'm trying to present some findings to people who don't really or are not comfortable with numbers. Then I'll use a visualization. But day to day, I rarely graph things. So the graphs are not the important thing. The important thing is what's in the clusters. So here are the clusters it has come up with. And I didn't tell you this, I should have. This is real DNS data from a real environment. Looking up here, and this is, by the way, part of a dashboard. I mean, not this notebook I'm showing you, but we have this as a dashboard. Our SOC team members and threat hunters have access to this dashboard. They periodically look at this dashboard and they can see live how things are currently clustering with things like DNS queries. In this case, even looking at the anomalies, the -1, there are some things in here that are very interesting. Now, that's not always the case. So I'm not going to use these as the example. I want to show you what's in the other clusters. So in the dashboard, we don't need to see all 500,000 queries. I'm only seeing a handful of the kinds of queries that are in each cluster. I would love it for a human to look at every query, but who has the time for that? Who has the employees for that? I would love to have filters or signatures that can tell me everything that's bad, but how quickly do domain names change? That's just not practical. We will always be behind. But now I can look at this first cluster and say, is there anything interesting there? And not really. Nothing that motivates me to dig more. Or in this next cluster, these are named service queries within a Microsoft domain. Not interesting. Here's internal hosts trying to find where the logs go. Not interesting. But look at this cluster here. These are wildly different. Now, I think that, I don't actually remember, I think, yes, these are in a thing called a data frame. That's where all the data is. So let me go and grab the data that's in row 54220. Let's just have a look at one of these things. There it is. And let's grab the actual query. Let's take a look at what that is. There we go. So this is very clearly an anomalous DNS query. This is, and if you're looking over here, some of you, especially incident responders and SOC people, are going to look at that and say, that's known bad. That's a DNS covert channel. And in fact, I used this particular data because I knew this organization had a compromise where a backdoor was installed, a covert channel was installed. The great thing, though, is that we can find this data without knowing it's there, without having the signature, because the machine can learn how things are related. There's lots and lots of other ways we can apply this. I want to show you just one more, and I need to leave a little bit of time to talk about this new thing that's coming out very soon. So let me see if I can do this in about 5 minutes or so. When it comes to doing threat hunting, when it comes to applying AI, there is no one solution. If you were here during the pre-game show, I was saying that generative AI is fascinating, but has almost no application for me in threat hunting. But AI and machine learning absolutely do. So I want to talk a little bit about that. I want to talk about how it is we can find anomalies in logs. I want to give you a way that that can be done without further burdening your poor SIM operator, who we always go after him when there's an incident. Is the data, it's in the SIM. Why isn't the SIM telling us about the bad thing was happening? Because no one told me that was a bad thing. We don't know that's bad till it happens. And now we have to go and write a query, and poor SIM operators, they are really overworked people. But I think there's a way to make this better. I want to give you a very brief introduction to a technology called an autoencoder. So an autoencoder or a one-class encoder, it tends to have this kind of design. It's sort of this hourglass shape. For now, just accept that as true. In reality, it need not have this shape. It's just the shape we traditionally use to talk about it. The thing that is most important is that it's got this choke happening in the middle. The goal in training one of these is that you're going to put data in on the left-hand side. Let's say maybe I put in a chair. And the goal is for the network to learn some representation down in that little choke there, those four little circles, that it can then use to reconstruct the chair on the other side of the network. So we're letting through a very little amount of information, hopefully being able to reconstruct the chair. And while I don't have the same chair, I do have something that's chair-like. And if I train it with lots of chairs, this too, it's a different chair, and the chair coming out is not the same chair, but it's chair-like. It's got all of the important qualities of a chair. Once we've trained an autoencoder, so for instance, this one, it can find chairs. If I put in something else, how different is the output? And in fact, in autoencoders, we talk about not how accurate we are, but instead we think about what the loss is, what the error is, the reconstruction loss. How far away from a turnip is Dwayne "The Rock" Johnson? Now, this is not casting shade on Dwayne. Dwayne is an incredible human being. If you have not read about him, read on. This guy is a really good human being. He is about as far from a turnip as you can get. So the reconstruction loss here is absolutely enormous. What does that have to do with our topic here? Well, let me come on back to my notebooks here. I've got a second one. This one, I'm going to load in some log data. So think about that sim operator. How do we know that an entry is interesting? How do I know an entry is unusual? Now, I'm not saying that I can automatically find things that are bad, but I can absolutely train an AI to tell us when things are unusual. And that in itself is useful. Here I've just loaded in a little bit of data. This is a real log out of a real system. And what we're going to do is try to train the AI so that we can figure out how well it reconstructs the log data. Because if it reconstructs it well, that log entry is normal for us. But if it has a very high loss, a reconstruction error, then it's not normal for us. And I'm going to do a little bit of tinkering on this because I'm looking at that timestamp, and anything that changes is going to increase this reconstruction error. That's okay, but the fact that the timestamp is changing isn't really interesting to me, so I'm just going to chop those off because that's like needless noise that we're creating. And I'm going to simplify it a little bit more too. I'm also going to pull out things that are not letters. Now, as I go through this, I want to be really crystal clear. I want to be upfront with you. I'm going to approach this from the point of view of reconstructing the log as letters, which is not how I do it in practice. I actually do it at the word level. It's much better at the word level. But there's a reason I'm using this other approach. Now, someone is asking, what are the system resources necessary for this kind of analysis? For this, once this is built, so building it, it's a few minutes, this is maybe 5-10 minutes to train, but then using it in operations, it's very fast. You are best served sending log entries in batches because each time you crank the network up, that's going to be slow. But if you send the data through at, 100, 1,000 at a time, the performance is quite good. And you can achieve near real time with limited system resources. In any event, so I'm just going to look at the character level. I'm going to make a couple of assumptions here, like I'm going to deal with 61 characters. I'm coming up with that because of how neural networks work. Again, that's a deeper topic, something we don't have time for. But I'm going to take that data, train the network, which I've actually already done. So this is kind of like a home cooking show. So it's already in the oven. I've already trained it, but it's this network right here. And what it'll let me do is to then take test log entries. Now, these entries I have here, these log entries are completely fictitious. And they're definitely anomalous. I mean, they're fictitious, so they're anomalous. Failed login attempt by Margie. That's not a normal event. Unknown operand from system out of disk space. The reason I know these are anomalous is that I manually wrote them, but they sound good. They sound like real system logs. So let me process those with the neural network and show you how these work, show you why it is that I'm using these characters. The first couple of log entries I've got here, the top is the actual log entry. The bottom is the reconstructed log entry from the neural network. And the question is, how far away is the reconstructed version? Well, the first one, I think it's exactly right. This looks really good. This is off. Oh, it's off by two characters are wrong. They are very close. Here's how the other log entries look. How far away are those? So we're looking at it visually and we can see, I mean, these are not even close. It doesn't matter that it was the same name. We're not even close. And the further we go, the worse it gets, because these are anomalous for that system. This is really easy to grasp. And we're looking at it as letters here, but this would just be converted into math, representing what that error, what that loss is. That's the kind of way that we apply AI in cybersecurity and using it for threat hunting. So we have in our organization, going back to James's question, we have not used AI to replace anybody. But what it has allowed us to do, it's allowed our operators to operate much more efficiently and spend much more time on problems, because the AI solutions are going and finding interesting things. It's almost like sending a dog off to go and fetch something interesting and bring it back, and you can decide whether or not it's useful to you. I want to take just a minute before I wrap up and discuss a new project that's coming to GitHub soon. So we've been in the process of negotiating and talking to, finding some backing for this project. And I think we've got that locked up now. So I'm willing to speak publicly about this. If you think about your organization and you think about security standards that you have, if you have any kind of code development that happens in your organization, you know every standard says you are supposed to be doing peer review of all of those code changes. Who's doing the reviews? How well are they doing them? What are they looking for? Do they even know? Which changes get the most stringent review? I've got a solution for you. So what we're pushing out in the coming months, probably about 2 or 3 months from now, is building an AI that acts as a webhook for you. There are people who are trying to solve this kind of problem using large language models, but I think it's wrong-headed. Large language models are amazing and they're generative AI, but that's not what this problem is. What's happened, I think, is that we've got this really big hammer called LLMs, and every problem we see, we've got to try to whack it over the head with that LLM hammer. And I'm not sure it's the right way to do it. So what our solution does is we're leveraging AI and machine learning by taking the source code, whatever the source language is, and compiling it halfway. Now, if you've ever done any language design or taking a programming languages class, you're familiar with the notion of an abstract syntax tree. That's kind of a technical thing. That's kind of what we're doing. That's halfway. So we turn it into an abstract syntax tree before it becomes the bytecode. We're stopping at the abstract syntax tree. And then we're training, so this is the AI and machine learning part, training vector embeddings, so that we can then store, we can represent those embeddings in a vector store. And the way that helps us is the vector store we provide has the vectors for all of the known code involving CVEs where vulnerable code has existed. So now we can take our code changes every time code changes are submitted with a webhook and automatically look up to see if there are any known vulnerable patterns in that code without using signatures, without using code scanning, without a human having to look at every one. We still need the human review, because now those changes can be flagged for special review because they're security impacting. Anyway, I am trying to come up with a name for that project. So if you've got an awesome name for that, put it in the Slack channel. I'm really interested. If you have questions about what I've talked about, please feel free to reach out to me. I'll be monitoring the Slack channel for a little while. If you're interested in doing this yourself, if you need this capability, we've got a QR code that'll take you to information about the Sec 595 class. Rob, thank you so much for this opportunity. I will hand it off.